All right, let's jump right in. Welcome to today's Explainer, where we're going to unravel what are essentially the invisible threads of the modern world. We're talking, of course, about Bluetooth. It's one of those things we all use literally every single day, connecting our wireless headphones, keyboards, smartwatches. But how often do we actually stop and think about how it works under the hood? Well, today we are going on a really fun, highly structured journey. We're going to zoom all the way from the everyday gadgets you're probably holding right now, straight down into the microscopic, bare metal engineering of data frames and radio frequencies. So if you're the kind of person who loves understanding how things tick, you are absolutely in the right place.
So here is our roadmap for today. We'll kick things off with Section 1, the evolution of Bluetooth technology. Then, in Section 2, we'll break down piconets and scatternets. Section 3 is all about pairing versus bonding. Section 4, we'll dig into the Bluetooth protocol stack. And finally, Section 5, we are going to zoom right inside a Bluetooth frame.
Okay, starting things off with Section 1, the evolution of Bluetooth technology. Before we get into the hardcore engineering, we kind of need to establish what Bluetooth actually is at its core. To really wrap our heads around Bluetooth, I think it helps to compare it to something else we use constantly, which is Wi-Fi. Now, Wi-Fi is essentially designed to provide internet connectivity to a whole bunch of devices all at once, right? Usually routing through an access point or a router. Bluetooth, on the other hand, is completely different. It's a short-range wireless radio tech operating on the 2.4 gigahertz frequency band, and it is strictly designed for one-to-one host-to-peripheral communication. You don't need a router, you don't need a network infrastructure, it's just your phone talking directly to your headphones, or your PC syncing directly to your mouse. It deals with smaller amounts of data, but with incredibly low latency. And it's actually kind of wild how fast this tech has evolved since Ericsson first cooked it up back in the 90s. Back in 1999, version 1.0 gave us a basic 1 megabit per second connection. But the real game changer, like the absolute turning point, happened in 2010 with version 4.0. That introduced Bluetooth Low Energy, or BLE. It drastically dropped power consumption and essentially gave birth to the modern Internet of Things, letting little sensors run for months on just a tiny coin cell battery. Then, 2016 rolls around, version 5.0 doubles the speed and literally quadruples the theoretical range to 240 meters. And jumping ahead to 2024 and beyond, version 6.0 introduces channel sounding. This uses phase-based ranging for highly secure centimeter-level precision. It's literally the global standard that makes things like digital car keys secure enough to trust.
Moving right along to Section 2, piconets and scatternets explained. Now that we know where it came from, let's look at the architecture. How do these gadgets actually organize themselves in physical space?
In Bluetooth lingo, a single network is called a piconet. Think of it like a tiny, localized solar system. You have a master device, let's say your smartphone. This master dictates the timing and the frequency hopping, and this single master can connect with up to 7 active slaves all at the same time. We're talking your smartwatch, your wireless earbuds, maybe a fitness tracker. But here is where it gets really cool. A device can actually be a member of 2 different piconets at once, basically acting as a bridge between them. When you link multiple piconets together like that, they form a physically extensible network known as a scatternet. It's just brilliant.
But that brings up a huge question. How do all these devices in a scatternet talk on this super crowded 2.4 gigahertz band without just completely drowning each other out? Well, they use a technique called frequency hopping spread spectrum, or FHSS. Classic Bluetooth takes that radio spectrum and slices it up into 79 different channels. The paired devices then jump across these channels in perfect lockstep, changing frequencies at a blistering rate of 1,600 hops per second. 1,600 times every second. This constant hopping is exactly what allows your Bluetooth connection to weave through interference, ensuring your podcast doesn't just stop playing the second someone turns on a microwave. All right, let's transition over to Section 3, pairing versus bonding. We've got our network architecture down, but how do these devices actually establish trust? I really want you to think about this for a second. You've connected to a BLE device. Great. Now what? Well, if you just want to read public, non-sensitive data, you may be totally done. But if we're talking about private health data, sensitive controls, or long-term relationships between devices, a simple connection just doesn't cut it. You need security. And this is exactly where 2 very specific and honestly often confused terms come into play. Let's clear this up right now. Pairing is all about ephemeral trust. It's the process of negotiating a security method, swapping some keys, and encrypting that current session. But the catch is, once you disconnect, those keys are gone. Poof, forgotten. It's like agreeing on a secret handshake for one single conversation and then pretending you never met.
Bonding, on the other hand, is retained trust. Bonding means actually storing those security keys produced during pairing, so the next time you connect, you start encrypted right out of the gate. You skip the whole pairing dance. So remember, all bonded devices have been paired, but definitely not all paired devices are bonded.
So, practically speaking, when do we actually need bonding? Well, it's an absolute must for wearables, smartwatches, or medical devices like a continuous glucose monitor. Just imagine the sheer user experience nightmare if you had to type a PIN into your phone every single time you walked to the kitchen and came back into range. It would be awful. Bonding completely eliminates that UX friction. And as a quick developer side note, it's super interesting how different operating systems handle this. If you're building an app for iOS, Apple's core Bluetooth manages bonds down at the OS level, so it triggers pairing totally automatically. But on Android, bonding isn't automatic at all. Developers often have to explicitly request it in the code using a command like create bond. Okay, moving right along to section 4, the Bluetooth protocol stack. We're descending deeper into the machine now, shifting from user-level security down into the bare metal software layers operating inside your phone. Let's basically trace the complete journey of your data. The Bluetooth protocol stack is fundamentally split into two halves. You've got the host stack, which deals with all the high-level data, and then you have the controller stack, which houses the incredibly timing-critical radio interface. So when you use an app at the top level, your request filters down through various protocols. For instance, you might use SDP, the Service Discovery Protocol, just to figure out what the device on the other end is actually capable of. Or maybe OBEX, the Object Exchange Protocol, to transfer a file. But all these upper-layer protocols eventually need a way to travel all the way down to the physical hardware.
So here's how that data cascades downward. Right below the application and upper protocols, we hit L2CAP, the Logical Link Control and Adaptation Protocol. I like to think of this as the beating heart of the whole stack. It takes the big chunks of data from the higher layers, multiplexes it, and chops it down into smaller, manageable packets. Below that is the LMP, which handles link management and encryption. Then we hit the baseband link controller, which physically maintains that PiConnect connection we talked about earlier. And finally, at the very bottom, we reach the radio layer, which actually modulates all that data into physical RF signals blasting out at 2.4 gigahertz.
And that brings us to section 5, inside a Bluetooth frame. We are now zooming all the way into the microscopic level to see what those physical radio waves are actually carrying through the air. This is the exact anatomy of the data flying around your room right now. A standard Bluetooth frame is broken up into 3 distinct parts. First up, you have a 72-bit access code, which identifies the master device and keeps everything perfectly synchronized. Next is a tiny 54-bit header, which we're going to decode in just a second. And finally, the payload itself. This can be anywhere from 0 to 2,744 bits long, and it contains the actual segmented data that just came flowing down from that L2 cap layer we were just looking at. Let's unpack that tiny header because, honestly, it is an absolute marvel of engineering efficiency. The header itself is actually only 18 bits long, but because error prevention is critical, it gets repeated 3 times, bringing the total to 54 bits. Inside those 18 unique bits, you have a 3-bit address. And think about this. 3 bits gives you exactly 8 combinations, which perfectly matches our PiCoNet limit of 1 master and 7 active slaves. It's perfectly designed. Then you've got a 4-bit type identifier, then 3 single-bit flags, F for flow control, telling the sender to pause if the receiver's buffer is full, A for acknowledgement, just a simple yes or no that the frame arrives safely, and S for sequence, a 1-bit toggle to detect if this is a brand new frame or just a retransmission. Finally, an 8-bit checksum to spot errors. It is mind-blowing that a mere 18 bits of data can flawlessly orchestrate the flow, the error checking, and the addressing of this massive wireless network. So as we wrap up this explainer, I want to pull all the way back out. Let's zoom out from those microscopic 1-bit sequence flags back to the macro world around us. Think about the incredible, seamless complexity happening in your pocket right this second. The automatic pairing, the 1600 frequency hops every single second, the L2 cap segmentation, all perfectly packaged into these tiny 54-bit headers. As you walk through your office or your living room or down the street, how many invisible PiConnets and scatternets are you walking through right this second? It is a fascinating, completely invisible web that holds our modern connected lives together. Thank you so much for joining me on this deep dive. Keep learning, keep wondering how things work, and I will see you in the next explainer.